In Theorem 4.2, we're going to generalize some of these properties that we observed in cyclic groups when we looked at 4 different examples of cyclic groups that came up in examples 3, 4, and 5. So let's see, what's the situation? So we have an element A in a group G, and that element has order n. So A has order n. That's important. And let k be a positive integer. Then what can we say about the cyclic subgroup generated by A to the k? From what we've seen, it looks like that subgroup is the same as the cyclic subgroup generated by A raised to the greatest common divisor of n with k. And we'll look at a few illustrations after we fill out all of this. Also, the order of A to the k then is n divided by the greatest common divisor of n with k. Okay. From this theorem follow 3 corollaries that are special cases. So if you're looking at the cyclic subgroup generated by A to the I, and you notice that it's the same as the cyclic subgroup generated by A to the j, then those are equal if and only if I and j have the same greatest common divisor with the order of A. So we can say that the second blank is filled in, or rather our blank for corollary 1 is filled in by saying those two groups are equal to each other if and only if the GCD of n with I is equal to the GCD of n with j. So we have the same greatest common divisor of those powers with n. Corollary 2 says, okay, now G is a cyclic group generated by A. Then G is equal to A to the k, so A to the k is a generator of our group if and only if. What can you tell me about the GCD of that power k with n? That has to be 1. So that power is relatively prime with the order of our group. And then lastly, the special case when we're looking at Zn. So an integer k in Zn is a generator of Zn if and only if the same thing is true. The GCD of n with k is equal to 1. So special case. Now I promised you to illustrate this theorem using the example 5 of rotations of the pentagon and hexagon that we just looked at. So according to our theorem, what is the cyclic subgroup generated by A squared? Well, that should be the same as alpha raised to the GCD of, what is n in this case? N is 5 because we're looking at the pentagon. So the order of alpha is 5. So n is 5. And then k is 2 because we're looking at alpha squared. Okay, well, what is the greatest common divisor between 5 and 2? That's 1. So the cyclic subgroup generated by A squared is the same as the whole group. So the one generated just by alpha itself. Same with alpha cubed. That's alpha raised to the GCD of 5 with 3. And that is also, the greatest common divisor is 1. So we also have alpha. And that would be the case for all other powers. So if we looked at alpha to the 4th, we'd get the same thing. Now, when we are moving on to the hexagon, we have n is equal to 6. Beta, that was our 60-degree rotation, has order 6. And we have a little bit more interesting things happening in this case. So when we're looking at the subgroup generated by beta cubed, what do we get? We get beta raised to the GCD of 6 with 3. Which the GCD of 6 and 3, that is beta cubed itself. Or the GCD is 3, so this is beta cubed, which was the group that had the identity in it and beta cubed. And with beta to the fourth, let's see what we find. The GCD of 6 with 4, the greatest common divisor between 6 and 4, that is 2. So we're getting the same subgroup as the one generated by beta squared, and that was the identity beta squared and beta to the fourth. And you can go back to the example and see, yep, that those two subgroups were indeed the same. And then beta to the fifth, we have beta to the GCD of 5 with, 6 with 5. That is 1, so we get beta. And that is, so beta to the fifth actually is a generator, just as beta was. So we get the entire group G2 of our rotations of the hexagon out of that. Now that illustrates the first part of the theorem, and then the second part has something to do with the order of these elements. So beta cubed, what's the order of beta cubed? Well, the order of beta cubed is, according to our theorem right here, it should be n divided by the GCD of n with k, so that is 6 divided by 3. So the order is 2. And indeed, we found that beta cubed squared is the identity again. So the order is indeed 2. For beta to the fourth, beta to the fourth, that would be, the order is 6 divided by the GCD, which is 2. So the order of beta to the fourth is 3. And the order of beta to the fifth, that is 6 divided by the GCD of 6 with 5, which is 1. So beta to the fifth has order 6. And what I want to finish with is the fundamental theorem of cyclic groups that tells us a little bit more about cyclic groups and also generalizes some of the things that we observed in the previous few examples. So the first thing is that when you're looking at a subgroup of a cyclic group, it's cyclic again. So every subgroup of a cyclic group is cyclic. And if you're looking at the order of a cyclic group, and that is n, then the order of any subgroup of a cyclic group is a divisor of n. And you can go back to the examples and find that that's actually the case. So all the subgroups of G2 were just had orders 2, 3, or 6. The third one, again, if the order of our cyclic subgroup is n, then for each positive divisor k of n, the cyclic group generated by A, has exactly one subgroup of order k. And that is A to the n over k. So those are 3 results that we will be using quite a bit, and they're important enough that we are actually calling this theorem the fundamental theorem of cyclic groups.